Hello everyone, it's your friendly hippie physics teacher once again. And this class I'm probably only going to be using it for my Regents Physics folks. Um, we're going to be talking about the dispersion of light today. We're going to be talking about the diffraction of light today. Um, and this is for Unit 12, Lesson 5 and 6. I'm kind of all mushing it into Lesson 5. And this is going to be our last lesson in this particular unit. Okay, so dispersion and diffraction of light. All right, the dispersion of light. It simply means the separation of light. Okay, now this can only happen if you have polychromatic light, all right, or white light. Okay, if you happen to have yellow light that comes from multiple light sources, that yellow light can be dispersed into the red and green wavelengths that are actually making it. Okay. But if you have a monochromatic source of yellow light, it cannot be dispersed. Okay. So dispersion, separation of polychromatic light into its component colors. All right. It is also the scattering of specific wavelengths of light by a medium. Okay, sometimes, for instance, the air scatters blue wavelengths of light more than other wavelengths that are passing through it, which is the reason our sky appears blue, because we're getting the scattered wavelengths from all over the sky. Otherwise, if that scattering didn't happen, our sky would appear black. Black. And the only light source in our sky would be the sun and the stars. Okay? That would be so weird. During the day, it would be warm, it would be nice, it would be sunny, but it would be black. Think about what the astronauts saw on the moon because they had no atmosphere. If our atmosphere did not scatter the blue wavelengths of light, primarily because that's what the nitrogen gas does, it would not appear that kind of blue and white and all of that mixture of color that we normally see during the day because of that scattering of light. Okay? Now, dispersion is what creates rainbows. Unfortunately, I don't have colored markers. Okay, but if you downloaded the notes, you will see this rendering in a nice Pink Floyd Dark Side of the Moon album cover format. Okay, but this is known as refractive dispersion as opposed to scattering dispersion. Scattering dispersion is like what happens in our atmosphere. It's like what happens with the laser when I put it through the jug of water that had milk in it, dissolved in it, and the light was scattering off of the milk particles that were in the water. Okay, this is refractive dispersion. And this happens because each wavelength of light that enters a refracting medium has a slightly different absolute index of refraction from all the other wavelengths of the light that's entering it. Okay? Interestingly enough, the relationship is that the longer the wavelength is, the more the refraction that's going to happen. Okay? So technically, the longer the wavelength, the higher the index of refraction for that wavelength. Okay, and so this is why if you take white light and shine it on a prism, this is some sort of, it could be glass, it could be plastic, some sort of transparent prism like this, you get what's called a double refractive effect. Okay, and even if you did it so that it only got refracted once and then came straight out, of the other side, you'd still get this dispersive, this separation of the wavelengths. Okay, so as it goes in, it gets refracted a little bit, the red, and the violet gets refracted even less. And then you go to the other side, and because you're going from high index of refraction to low index of refraction, it creates an even greater separation because the angle's getting bigger again. All right. Over here, it was bent toward the normal line, and you get that first separation. Over here, it's now bent away from the normal line, and you get an even further separation. And what you get is you get the violet on top and red on the bottom. Now, interestingly enough, when we look at rainbows, it appears reversed to us, but that's because of the geometry of how we have to look back at the light. And the geometry for us is the red light coming from the bigger angle makes it appear like it would be on top. The violet light coming from a smaller angle would make it look like it's on the inside of the arc of the rainbow. The reason that the rainbow is curved is because what's coming from the sun? A cone of light is hitting us. Okay, it's not parallel waves at all. It's a cone of light. And so we're seeing the edge of the cone that's being refracted by the water droplets that are falling when it's raining. Now, the rainbows happen because it's a combination of this happening inside the raindrops, and then that getting reflected off of the rest of the rain that's there. Okay? That's why you will never see a rainbow looking back at the sun through the rain. Won't happen. You'll always see a rainbow on the horizon that is away from the sun. The sun has to be behind you. Okay? You can do this with a garden hose. Okay? Say I've got a garden hose in my hand here. Okay? And if the sun is behind me, say up in the sky, it's mid-morning, getting toward noon, and I spray it so that I get the fine mist fan of spray that goes out, you can see the rainbow in the mist of the spray right there because the sunlight is coming down, it's getting refracted, double refracted through the raindrops, through the water droplets of the spray, and reflected off of other water droplets that are there. And it will always be at a specific distance and a specific pattern relative to that. Red on the outside, violet on the inside. Okay? And this same phenomenon can be seen through high cirrus clouds when the ice crystals act like prisms in the clouds. And this is the one time where you do have to be looking up and you'd be looking toward the sun. Don't look at the sun, look toward the sun. And you'd see this ring around the sun about, if you hold your hand out like this and you put your wrist at the edge of where you see the ring, the tip of your hand will be about where the center of the sun is. This angle right here is the angle that is produced by the rays of light getting bent, refracted through the ice crystals in the cirrus cloud. Okay? The rainbow that appears there, is because the ice crystals are refracting the light like prisms. Okay? So dispersion, refractive dispersion, is what's going on when the white light from the sun is getting refracted by raindrops or ice crystals. And because it's white light, each wavelength of that light has a slightly different index of refraction for the water and the ice, and that creates the separation. Red gets refracted more than the violet. Okay? Red has a longer wavelength, so it gets refracted more than the violet light will. Okay? Now, diffraction. Diffraction. There is a phenomenon called double slit diffraction, which we use to analyze the wavelength of monochromatic light passing through it. You can also use it for polychromatic, but again, that diffractive effect, as it separates the wavelengths, the different wavelengths are going to overlap and create different areas of constructive and destructive interference. I am going to show you how this works using the PhET lab. And we'll go back to the PhET lab and look at it and look at it from the point of double slit diffraction. Okay. Interestingly enough, the geometry of how the light passes through the slits and the distance between the slits and a screen create a separation of the constructive and destructive interferences of the diffraction pattern from the two slits. As the wave bends through those slits, they create constructive and destructive interference areas, and you get the diffraction pattern we're going to describe and calculate as soon as I get my easel back up. This right here, lambda equals XD over L, is the double slit diffraction equation for small angles and large distances compared to the wavelength of the light that's getting diffracted. The D over here is going to be relatively small compared to the other two numbers here. X is going to be large, can be anywhere from, that sort of distance to, if you got a really long L here, it's going to get really wide. Okay. So lambda equals XD over L. This is the equation we would use to determine the wavelength and therefore the color of the light that was being diffracted through the diffraction barrier. Or this is what we would use to predict what the pattern would look like, where the pattern will occur, and how wide the pattern will be if we knew the wavelength of the light that we're going to use. This same equation will work for sound. It'll work for water waves. Anything that gets diffracted by a double slit diffraction barrier obeys this relationship between wavelength, separation of pattern, in other words, from the central maximum to the first order maximum, the separation of the slits in the barrier, and the distance from the barrier to where you're seeing the pattern, to the screen that the pattern is being shown on. Okay? Now, if this were sound, X would be the distance from where, if you stood in between two speakers, it would be the distance from there, centered between the speakers. You'd move over a little bit, you'd hear the sound get softer, and then you move over a little bit farther, you'd hear the sound get louder again. That second spot to the left or right of center is known as the first order maximum. For sound, it means it's a louder sound. Right in the center, you get the most mixing, you get the most constructive interference. Boom, that's where the central maximum is. It then creates destructive interference half wavelength away, and that half wavelength corresponds to half this distance. Okay? And then moving over a little farther, you get back to the next maximum, where that's my X distance. Okay? Water waves can do the same thing. Let's say you have two openings in a harbor, and you have a storm that is blowing in waves toward the harbor and the seawall. Well, that can create a constructive, destructive interference pattern in the harbor. And so at the shore, the distance between where it's constructive interference and the next constructive interference of those ocean waves, that would be this distance X here. L would be the distance from the seawall into the shore. D would be the distance between the two openings in the seawall. Okay? wavelength would be the wavelength of the ocean waves that were coming in and hitting the seawall, and then the little bit of it going through the opening. Okay? So this can be used for a lot of applications. Alrighty? So, like I said, dispersion, we have two varieties. The big one that everybody most commonly encounters is the refractive dispersion, where white light gets separated into the all of the colors of the rainbow. Okay, you can get scattering dispersion, and that's what happens when light is physically reflected off of particles within the medium, and those particles respond to specific wavelengths more than another. That's what's going on in our atmosphere, and that's why the sky is blue. Okay? Diffraction, remember that's the bending of the wavefront to fill an empty region of a medium beyond a barrier. So if I put two of those openings, it's going to create two patterns, or it's going to create one pattern of the two sets of waves that are getting diffracted through that. You get constructive interference. The center constructive interference is known as the central maximum. The next constructive interference part of the pattern to the left and right of the central maximum are called the first order maximums. And using that equation, lambda equals xd over L, we're able to use this pattern to determine the wavelength of the light that's being diffracted. And we'll be using the PhET lab. I'll be using the PhET lab and showing you the particulars of it when we do our online session following this video. Thank you very much for your time. And this is your friendly heavy physics teacher. One more time, signing off. Let's see. For those attending the reverse parade, I will be there. Maddie, I will be there. Okay. I am clearing my decks and making sure that I have the free time to be there. All right. So we'll see you there. And hopefully the world will figure out how to deal with this COVID-19, and we can get back to being in the classroom again. Thank you very much. Have a great afternoon.